Hello, good morning everyone. I am now going to present to you another topic about the normal curve, about the normal distribution. This is the areas under the normal curve, understanding the z-scores. The normal distribution depends on two parameters, the mean and the standard deviation. So in any given problem about standard normal distribution, we always have to look for the mean and the standard deviation because the values of the z-scores as well as of the areas and percentage under the normal curve depends on these two values. Since we have different mean and standard deviation from any data set that we are gathering, and if we are going to plot them one by one, it would be tedious on our part. That is why we have what we call the standard normal distribution, wherein all of our normally distributed values will be transformed into a uniform curve. That is why it is called a standard normal distribution. So there is no more need for us to draw the normal curves for the different means and standard deviations that we got from different data set. So we are going to standardize all of our data set which are normally distributed and transform it into an all size or all fit one size fits all, rather a one size fits all normal curve that is good for all of these kinds of distribution. So the process of transforming all of those data set which are normally distributed to a standard normal distribution is what we call a standardizing. That is why we have the z-scores. The z-scores will represent the standard scores of the raw scores that we have gathered from different normally distributed data set. The process of converting a value from a normal distribution to a value of the standard normal distribution is called standardizing, and this requires the use of z-scores. So what is a z-score? Z-score, also known as the standard score, is the measure of position that indicates the number of standard deviations a data value lies from the mean. So this is also related to our lesson about the empirical rule that we have discussed last time. The distance of a standard deviation from the mean. But this time we're going to standardize it. So what is the calculation for the z-score? From the raw scores that we have gathered from any data set which is normally distributed, we can transform it into a standard score by getting the difference of that particular raw score from the mean. So that is your score minus the mean, which is the mu, divided by the standard deviation, which represented by the small letter sigma. That is the formula for calculation for z-scores. And take note that the z-scores are rounded off to the nearest hundredths, so 2 decimal places. So if you're going to put that into the normal curve, so we can have a mean of 0. So all of the mean will be transformed into 0. So the distance that you are going to travel above the mean or to the right will be positive values, but on the other side we have the negative value. So this is just like a number line wherein 0 is at the center, then all the values to the right are left, to the left are negative. So this is the bell shape, the normal distribution, the standard normal distribution. So all of the normally distributed distribution or data set can be transformed into this kind of data set. So the mean will become 0. When you standardize a variable, its mean becomes 0 and the standard deviation becomes 1. So that's why we have 1, and we also presented the 0.5, half of it, on the left side and on the right side, so that it can be clearly seen that all of the values are represented in our normal curve. So the areas under the normal curve, so visiting the empirical rule, we have learned from our discussion last time that it has limitations because it can only give us estimation on the following values: 68%, 95%, and 99.7%. And these are just approximate. So what will be the case if our area is not exactly 68%, 95%, or 99.7%. So the empirical rule cannot give us the exact value for that. That is why we have the z-scores that can help us locate anywhere within or under the normal curve. So that is the good news of having this kind of lesson. So the area or percentage or the proportion of probability is a decimal value between 0 and 1. This is pertaining to the characteristic of the normal curve that we have discussed last time, that the area under it is equivalent to 1 if you are talking about the overall area. So the highest value that you can give is 1. If there is no area at all covered, then the lowest value that we can give for the answer is 0. So it's between 0 and 1. This is just also true with the probability. If you are going to answer probability problems, the values that we can give are from 0 to 1. And you can actually see the values using the table. That's why we have to use the z-score table for this particular topic. And the tables were already presented to you beforehand. So this is the table. This is just a part of the table that I just presented and I just captured for us to understand what is the meaning of this table and how to use this table. So the z values or the z-scores are actually plotted here. That's the first decimal place of the z-score. And the other part on the first row of the table, you have also the second decimal place of the z-score. As I have mentioned earlier, the z-score must be converted into the nearest hundredths or 2 decimal places. So after that, you're going to find the values at the center at that particular region of the table. So this table yields probability or area starting from negative infinity, that is from the left, going to the right of the needed score. So this is now the concept of the table. If you are going to look at the numbers, these are actually percentages which are converted into decimals, and it means that these are the areas covered from the left of the curve going to that particular z-score that you are talking about. So for example, you are dealing with a z-score of 1.89. So I am talking about the very last cell in this particular example. So 1.8 for the first column, you have to look at 1.8, and then 0.09 for the row, because I'm talking about 1.89. So that is the example of the area or of the z-score, so 1.89. The intersection of that is 0.9706. So it means that the area covered is 0.9706, almost 1. So the area covered is from the very left part up to that particular value, 1.89. So the area covered is 0.9706. So that is the concept of the table that we are using. There are also other tables available. There are tables that expresses the area of the normal curve starting with the center and so on. But the table that we are using right now is starting from the negative infinity going to the z-score that you are trying to solve. So I hope that's clear with you. Let's have the first example. Find the area of a z-score below 0.36. So using the table, you can actually get the answer directly. If we are going to visualize what is the meaning of this question, the area of a z-score below 0.36. So since we already standardized our normal curve, so we are now using the z-score, not the raw score anymore. So if 0 is at the center, that is the mean. So we're going to find 0.36. That is on the right side of the mean. So this is now the red line that represents 0.36. And the problem is looking for the area, find the area of that particular z-score. So the yellow colored region represents the area that is the answer to this problem. So using your table again, we're going to get a parcel of that. Since the z-score is 0.36, so on the first column, we have to look for 0.3, the first decimal place. And for the row, we have 0.06 to make it 0.36. So here is it. The intersection of the two is 0.6406. So it means that this yellow colored region is 0.6406 of the overall normal curve. So that is the area covered. We can also transform that into percent, 64.06. So this means that the area below 0.36 is 64.06%. That is how to use the table and how to interpret the z-score. Example number 2. This is a worded problem. A normally distributed population of college entrance tests has a mean of 80 and a standard deviation of 5.2. Find the percentage of scores that falls below 73. So we don't have the z-score yet for this particular example because this is actually the data that we have gathered from our survey. We all know that the mean is 80 and the standard deviation is 5.2, and we have to get the percentage of scores that falls below 73. We can never use the standard normal distribution for this particular problem because this is not standardized. So what's the first thing to do? We need to standardize this by converting our score 73 into its standard score. So we need to compute for the z-score of 73. So here is the computation. 73 will be deducted by the mean, 80, and the result will be divided by the standard deviation, 5.2. As the formula suggests, z-score is equal to the raw score minus the mean divided by the standard deviation. That gives us negative 1.34615. And since our z-score should always be rounded off to the nearest hundredths, so we will have the two decimal places, applying the rules for rounding off, we can have negative 1.35. So 73 will now be replaced by negative 1.35, and from this particular distribution on your left, this is the raw score. We can never use the standard distribution for this. So that will be the problem. We can never identify the area. So now that we have applied the z-score, we can now look at the table, the diagram on the right. So from 73, we have actually located the position in the standard normal distribution that is found on the left side of 0 of our mean. So the red line shows the position of 73 in the standard normal distribution. That is represented by negative 1.35 approximately. So because of this, we have already the number. We can compute for the percentage of the scores that falls below it. We will get again our table and locate the z-score, negative 1.35, rounded off to the nearest hundredths. So I just got the portion for negative 1.3 and 0.05. So the intersection of the two will give us the area for negative 1.35. The area under that particular z-score. And that is 0.0885. So that is already the answer to this problem. Or we can convert that into percent. 8.85% of the scores falls below 73. So if the question is how many of these students got below 73, so we can actually get the answer. If we know the number of examinees, and then we can compute 8.85% of them, then the number will be representing those who got below 73. That's our second example. Our third example is the same. Given we have the entrance examination, which is a normally distributed population and sample, then the mean is 80 and the standard deviation is 5.2. Find the probability that an examinee got a score between 82 and 86. So the region that you are going to locate is between 82 and 86. What is the percentage of that particular region? And if you will know the percentage, you will answer the probability of the examinee that got the scores between 82 and 86. So again, this is not standardized. The first thing to do is to convert our values 82 and 86 into z-scores. So here are the computations using the formula. The z-score for 86 is 1.1538. That is 1.15 to the nearest hundreds. The z-score of 82 is 0.3846. That is rounded off to the nearest hundreds, 0.38. So we will just look at the diagram on the right because that is already the standard normal distribution, whereas the one on the left is not the standardized form, but they are of the same form. So we need to locate the region that is colored green. So what is colored green? We need to get again our table, and to get the area of that particular region, we need to get first the area of 1.15. After that, we will get the area of 0.38. The difference between the two logically will represent the area between the two. So here is it. For 0.38, the area is 0.6480, while the area for 1.15 is 0.8749. The difference between the two, logically again, will represent the area that is between. We don't need to get the other areas from the left side of the curve. We are only interested on the area between the two z-scores. So we have to get the difference. 0.849 minus 0.6480 is 0.2269. That is equivalent to 22.69%. That is now the answer. So the probability that an examinee got a score between 82 and 86 is 22.69%. Example number 4, the same given. Find the percentage of scores that lies above 73. So this time, if we are going to visualize it, we are talking about the area above. So the z-score is already computed there. 73 is equivalent to negative 1.35 as we have already solved in example number 1. But this time, the shaded region must be on the other side. That represents the scores that lies above. So when we say above, it's on the right side of that particular line, the red line. So we are talking about that region. So if we are talking about that region and our table is giving us the area from the left side, so we need to do something. So we need to subtract our value from 1, knowing that the overall value of the normal curve is 1. So I hope you got it logically. So take the total area under the normal curve, that's 1, and subtract the cumulative area to the left of the z-score, and that will be the area of the right side. So that is the logical explanation why we are using 1 and subtracting a particular number from it, because we are trying to get the other side of the curve, the area of the other side of the line. So that is 73, the circled one. That's the area that we are trying to get because we are getting above 73. So from the z-score, negative 1.35 again, negative 1.35 is 0.0885. But that particular region is on the left side. That's the answer to example number 1 a while ago. So we are trying to get the other side, the area or the percentage that is above that negative 1.35. So that's 1, the overall area, minus the area below it or on the left side, that's 0.0885. So the remaining value is 0.9115 or 91.15%. So that is the area or the percentage of the scores that lies above 73. So that is the answer. Example number 5, a normally distributed population of college entrance examination is still having the mean of 80 and a standard deviation of 5.2. This time we're going to get a probability that an examinee got a score below 82 or above 86. So you are talking about the regions below 82 and above 86. So we have to get the areas of these two regions. So graphically, we are talking about the shaded areas on this particular diagram. So the gray colored regions are the areas that we are trying to get. So if that is 82 there and 86 is also there, so between them is not the area of interest, but the areas outside of those particular scores. That is for this particular example. So how do we get this one? So this is a bit tricky. So if this is the problem, this is what you do. Again, you have to get the z-scores. You have to standardize 86 and 82, and we have already solved these numbers a while ago. 86 is 1.15 and 82 has 0.38 as the z-scores. And we have already located that in our table. So the regions or the areas are the following. So the arrow tells us that from that particular point to that particular point, the area is 0.8749 because that represents 86. 0.38 has the area of 0.6480, as we have already solved also in the previous example. So graphically, that represents this area from the left side going to that particular point. You can locate that using the blue arrow. That area represents 0.6480. But the question is, what is the area that is colored gray? So how do we get that? So if we are going to subtract 0.8749 and 0.6480, we will get 0.2269. And that is not the answer because that is the area between this particular z-scores. So that is the area that we are talking about. That is not the answer. We are talking about the area that is outside 0.2269. So logically, we need to subtract from 1 because the overall value or the area of the normal curve is 1. So 1 minus 0.2269, the answer is 0.7731. Another alternate solution is we can get the area, the remaining area that is on the right side. How do we get that one? That 0.1251. So since we already got 0.8749 as the area from the left side going to 86, so what is the other part that will give us an overall area of 1? Because the overall area of the standard curve is, normal curve is 1. So that is 0.1251. If we are going to check, 0.8749 plus 0.1251 is equal to 1. Therefore, this shaded part here on the right side of the curve is 0.1251. Plus, the area that is also on the other side that is shaded is 0.6480. So if we are going to add the two, that's 0.7731. So we still get the same answer. So either way, we can get the same answer, 77.31%. So that's 0.7731 or 77.31%. That is the probability or the percentage that an examinee got a score below 82 or above 86. So those are the things that we are going to do if we are trying to get areas from different regions under the standard normal curve. So still have a lot of exercises to be answered, and that will be given to you as your seat work. That's all for now. I hope you have learned something. If you have some questions, to just give me a message. Thank you so much for your time.